All right, everyone, get ready, because today we're going deep into the world of Livermorium. Now, this isn't an element you'll just stumble upon. It's synthetic, a real heavyweight in the world of chemistry. And we're going to see what its Wikipedia page has to say about it. So let's get this deep dive started.
What I find fascinating about Livermorium is that it's right on the edge of what we know about matter. It really makes you think about how atoms are structured. You know, the nucleus is made of protons and neutrons.
Yeah, for sure. Basic building blocks.
Right. Well, as you pack more and more protons and neutrons into that nucleus,
Yeah.
it gets kind of unstable, like a house of cards in a windstorm. Livermorium's nucleus is so packed, it's right on the verge of breaking apart. That's why we call it super heavy.
So it's not just about finding a new element. It's about pushing the limits of atomic structure.
Exactly. And to even create Livermorium, scientists have to overcome huge challenges.
Yeah.
It's not like mixing chemicals in a beaker.
Yeah.
You have to actually fuse the nuclei of a lighter element.
Fusion, isn't that what powers the sun?
It is. And there are a couple of ways to do it. Hot fusion is like a high-speed collision, smashing atoms together with a ton of energy. Imagine two cars crashing head-on at 100 miles per hour. You might get them to stick, but there's going to be a lot of debris.
So that's where the neutrons come in. The nucleus is shedding weight to stabilize.
Precisely. Now, cold fusion is a bit gentler, more like a slow merge. But either way, you're trying to force those positive nuclei together to make a new element.
So how did they make Livermorium? Was it a first try thing?
Oh, definitely not. Making Livermorium was a long road with lots of setbacks, even a bit of drama. The Wikipedia page mentions early attempts way back in the 1970s, but they couldn't detect any atoms of Livermorium. And then there was that claim in 1999.
What happened?
Well, a group of researchers said they had created Livermorium using lead and krypton. It was huge, published in all the big journals. But then, it turned out, the data was made up. A real blow to the field.
Wow, a real roller coaster. So when did they actually make Livermorium?
The year 2000 was the big breakthrough. Scientists at the Joint Institute for Nuclear Research in Russia finally managed to synthesize it by fusing curium and calcium. But here's the thing. They only detected a single atom.
Just one. How could they be sure it was Livermorium?
Pretty clever how they do it. Livermorium is so unstable it decays really fast, emitting an alpha particle. And each alpha particle has a unique energy signature, like a fingerprint.
So like a trail of breadcrumbs, but leading to the element instead of Hansel and Gretel's cottage.
Exactly. Scientists know what these energy signatures should be, so when they see an alpha particle with the right energy, they can trace it back to its source.
That's incredible, like atomic detective work. Now, the Wikipedia page mentions this island of stability. What is that?
The island of stability. It's a fascinating concept in super heavy element research. Remember how those super heavy nuclei are really unstable?
Yeah.
Well, scientists think there might be a sweet spot. Certain combinations of protons and neutrons, that could lead to super heavy elements that are actually stable.
So some of them might actually stick around for a while.
Exactly.
Like a safe harbor.
Yes.
So where does Livermorium fit into this? Are we on the island yet?
Not quite. The Livermorium isotopes we've created are still really short-lived. But what's exciting is that each new isotope gets us closer to understanding these extreme atoms. And maybe closer to that island.
So every experiment is like mapping the periodic table.
Exactly. And Livermorium is right on the frontier.
This is amazing. We've talked about how it's made, but what about what it's like? Is it a metal, a gas, a liquid?
It's understandable to be curious, but studying Livermorium's properties is tricky. It's like trying to study a soap bubble before it pops. It doesn't last very long, but we can make some guesses based on its lighter relatives, the other chalcogens like oxygen and sulfur.
So we're looking for family resemblances.
Exactly. And just like families, there are similarities and differences. We expect Livermorium to share some traits with the other chalcogens, but with some unique twists because of its size and something called relativistic effects.
Relativistic effects. Did Einstein just enter the chat? I thought we were talking about chemistry.
It's wild. When electrons move as fast as they do around Livermorium's nucleus, Einstein's theory of relativity comes into play.
So it's not just where the electrons are, it's how fast they're moving.
Exactly. And these relativistic effects can change how Livermorium's electrons behave, making its chemistry much more complex. Unpredictable. It's one of the things that makes Livermorium so fascinating to study.
I'm already feeling my brain stretch. This is incredible. Tell me more.
Before we get into those relativistic effects, let's talk about how scientists actually study Livermorium. I mean, we're talking fractions of a second here.
Right. It's like trying to study a firework that's already exploded. So how do they do it? Does the Wikipedia page say?
It does. Direct observation is tough. but scientists have found some clever ways to learn about it. One way is to study its lighter relatives, elements like bismuth and polonium.
The family resemblance strategy again.
Yeah. Exactly. The Wikipedia page actually gives a great example. Back in 2011, researchers were trying to make other super heavy elements, nihonium, fluorovium, moscovium, using targets made of americium and plutonium, bombarding them with calcium ions.
Okay, super heavy element smash up. Where's the Livermorium?
Right. Well, the targets had some impurities, lead and bismuth. It wasn't intentional, but it was a lucky break. They ended up making some new isotopes of bismuth and polonium through something called nucleon transfer.
Nucleon transfer. Remind me, what's a nucleon again?
Basically, it's just a proton or a neutron. So during this nucleon transfer, some protons and neutrons from the calcium ions got swapped with the lead and bismuth, creating these new lighter isotopes.
Okay, so accidental bismuth and polonium, how does that tell us about Livermorium?
Because bismuth and polonium are right above livermorium on the periodic table. They're in the same family. So by studying how these lighter isotopes behave, especially how they make compounds, scientists can make predictions about livermorium.
So they're using these lighter elements as stand-ins.
Yeah, like test runs. And what's interesting is that even these indirect experiments can give us surprises. The researchers who made those bismuth and polonium isotopes went on to study their hydrides, BH3 and POH2.
Hydrides, that just means they bonded them with hydrogen.
Right,
Right.
right. And what they found was that these hydrides were much more stable than expected at high temperatures. Now, this doesn't tell us exactly how a livermorium hydride would behave, but it gives us some clues.
So even though Livermorium is hard to study directly, scientists are finding creative ways to learn about it.
Absolutely. They're pushing the limits of what's possible.
So where does that leave us? We've got some hints about Livermorium, but what's next? Is it all about finding that island of stability?
The island of stability is definitely a big goal. Scientists are always trying new things, new reactions, new materials, trying to make heavier and heavier isotopes, hoping to reach that island of stability.
It's like exploring uncharted territory.
Exactly.
What are some of the things they're trying?
Well, one idea is to use controlled nuclear explosions to get the energy needed to create those super heavy isotopes.
Controlled nuclear explosions. That's intense.
It is, but it shows how far scientists are willing to go.
It makes you wonder, is there any practical use for Livermorium? Or is this all about scientific discovery?
It's a good question. We can't predict the future, but history shows us that fundamental research often leads to new technology.
So even if we don't have Livermorium in our phones anytime soon, it's still worth studying.
Definitely. The pursuit of knowledge is important.
So who knows what we'll learn from Livermorium?
Exactly.
We've talked a lot about how Livermorium is made and how it's studied, but before we wrap up, I wanted to go back to those relativistic effects you mentioned. They sound so interesting.
They are.
Can you tell us a bit more about them?
All right, so those relativistic effects. It's not every day you hear about Einstein in a chemistry conversation.
It's definitely one of the things that makes super heavy elements so interesting. Remember, we're talking about electrons moving incredibly fast, almost the speed of light around the nucleus, and at those speeds, Einstein's theory of relativity becomes really important. So it's not just where the electrons are, but how fast they're moving. And that speed changes how they behave.
Exactly. Think of it like a spinning top. You know how it wobbles a bit as it spins?
Yeah.
Well, imagine that top spinning so fast that it actually starts to change shape. That's kind of what's happening with Livermorium's electrons. Their speed and the pull of the nucleus create these relativistic effects, which warp their energy levels and can even affect how they bond with other atoms.
Okay, so how does this tie into that supervalent hybridization thing the Wikipedia page mentions? It sounds complicated.
It is a bit complex.
Yeah.
But let's try to break it down. Atoms like to have a full outer shell of electrons. It makes them stable. So they share electrons with other atoms to form bonds.
Right, like
Yeah.
how hydrogen and oxygen share electrons to make water.
Exactly. But with Livermorium, those relativistic effects kind of mess things up. They can change the energies of the outer electron orbitals, making some orbitals available for bonding that normally wouldn't be.
So Livermorium has some extra bonding options.
Yes. And this can lead to some unusual bonding arrangements. The Wikipedia page specifically talks about Livermorium hydride, or LVH2. It's predicted that the molecule would have a wider bond angle than you might expect.
Wider, so instead of being bent like water, it would be more spread out.
Exactly. And that wider angle,
Yep.
caused by those hybridized orbitals, could make the molecule more reactive or change how it interacts with other molecules.
So relativity can actually affect the shape of a molecule. That's amazing. But with all this talk about predictions and models, Will we ever be able to study Livermorium's chemistry directly?
That's the big question. And like with a lot of things about Livermorium, the answer is complicated. It's really hard to study because it doesn't exist for very long. But scientists are always coming up with new ideas and techniques.
So you're saying there's hope?
Of course. I mean, just a few decades ago, making elements like plutonium seemed impossible. But now we're creating and studying elements much heavier and stranger. Technology is always advancing. So it's possible that one day we'll be able to study Livermorium more directly.
That would be incredible. But even if we can't do that anytime soon, we've already learned so much from trying to understand Livermorium.
We have. It's pushed the limits of what we know about nuclear physics and chemistry. It's challenged our understanding of matter and the periodic table. It really shows the power of scientific curiosity.
It's amazing to think that even in the realm of the super heavy, the most fundamental science can lead to such incredible discoveries. Well, that brings our Livermorium deep dive to an end. My brain is definitely buzzing with new knowledge. It's amazing to think about all the mysteries of the universe that are still out there.
I agree. Thanks for joining us on this journey. Until next time, keep those minds curious. And remember, there's always something new to discover.